Okay, here we go. So last time we were talking about flux. So recall that a vector field can represent many different things. We talked about how vector fields can represent forces. Here, we're using a vector field to represent a fluid flow. And again, there's lots of different kinds of fluids. You know, we got air in this room. There's water in a pool or the ocean or something like that. The odd concept of animal migrations being a fluid. A little bit weird, but it's something you can do. So specifically now, we started off with the vector field representing velocity. And what we found is that the flow rate, just volume of fluid per unit time, is then computed by this really interesting quantity called flux, which is computed by this formula F dot n times A. And then we found that now there's a different point of view on fluid flow, and maybe we'll want to account for the fact that some fluids are more dense or less dense. And if you use this as a way to represent fluid flow, put this extra factor, density, in there. Right? It seems like, at a first glance, it seems weird to multiply these seemingly unrelated quantities of mass per unit volume and velocity. Seems strange, except if you do it, then, if you're interested in computing not volume, but mass per unit time, or quantity per unit time of your fluid, again, computed by the same formula called flux. Right? So, flux is useful for computing different things depending on how your vector field represents the fluid flow. But in both cases, flux is interesting. Right? Okay. Alright, so that's where we left off. And recall that I left it as a suggested exercise for y'all to actually do this calculation yourself. It's going to borrow dramatically from the previous calculation that we did go through. Okay. All right. So now I want to point out that there are more difficult kinds of fluids to deal with in some cases. So suppose you have a light bulb. I guess it's a blue light bulb, and the light bulb is emitting photons. And by the way, this is another kind of a fluid if you think about it. Light made up of a bunch of little particles, just like water is made up of a bunch of little particles. And if you have a light bulb on, it's emitting photons. That means that there is a flow of the fluid of photons emanating out of the light bulb. Okay. All right. So fine and dandy, no problem. Here's where it gets weird. Suppose you have a second light bulb that is also emanating photons, right? Another sort of separate fluid flow. Here's the thing. At points that are separated, distantly separated from both, there are two kinds of photons that go through that point. There are the photons at the purple point that came from the orange light bulb, and there are those who came from the blue light bulb. So how would I describe, right, if I wanted to have a single vector that describes what the nature of the fluid flow is at that purple point? Do I use the one vector or the other, or do I average them or something? I mean, how would I represent the fluid flow? I can't make any reference to the velocity because at this point there are two very different velocities. What do you do? Right? So I just want to point out there is a way to deal with this. The idea is to look at this formula that we've already established, that if you have a fluid flow represented by a vector field, right, that generates the ability to compute flow rates. So what do we do when we find ourselves unable to write down the vector field? And the tricky idea is just to say, all right, well, I can still compute flow rates, right? And if you know what the flow rates are by calculations that you can do, and what we say is that the vector field is whatever it has to be for the flux formula to correctly compute all of the flow rates. Yeah. So there is an answer in these cases for how to do that. Now, I think this is a pretty cool observation, and related to this, I wanted to show how you can use this idea to compute a vector field representing the flow rate out of a ball that is filled uniformly with a glowing gas. And first I'm going to just observe how unbelievably complicated this scenario is. It's ridiculously complicated. After all, there is a little particle of glowing gas right here, and it's emanating photons every which way. Right? But then there is also a particle of gas over here, and it is emanating photons every which way too. And so is every other of the countless particles of glowing gas emanating photons every which way, right? So wherever you might be interested in looking, if you're interested in looking at, let's say, this point right there, and you want to know, well, what's the velocity of the fluid there? Well, there's an orange photon going through that point. There are blue ones, and there's photons coming from everywhere within the gas cloud, all at that same point. And so how do we define the velocity? Can't do it, out of the question. How would we go about representing the fluid flow with a vector field? Well, we would play this trick right here, basically. And there are some clever arguments involved in how to actually make that happen. And we, as y'all know, find ourselves behind schedule and tough choices to be made about what to spend time on in class and all that. And I sadly, and it really does make me sad, this is a fun calculation. We're not going to be able to cover this. And then further sadly, this is not in the book. So I'm just going to have to scratch off this whole example. You're not responsible for it. Now, if you want to give it a look, because it is pretty cool, by all means, I'll happily answer questions about it in office hours, but it's not fair game material for the course, because again, we just have tough choices. We just don't have time. Okay. So anyway, moving along. So next thing, the book describes this thing called a flow line. It's actually kind of exactly what you would think it is. So the idea of a flow line is if you drop a particle into your fluid, and the particle goes exactly where the fluid tells it to go, right? Of course it does, right? So if the fluid is going that way, well, then the particle is going to go right along with it. So what then would be the path that the particle would follow? So the idea is this. The idea is that particle's path, position is a function of time, right? That we have a parameterization of the particle's path. What I have here, the derivative of that parameterization, of course, is the velocity of the particle. Right? And the velocity of the particle, as we just claimed, is going to be the velocity of the fluid. That's what the particle is going to do. The particle just floats right along and goes wherever the water goes. Right? So that's represented by the velocity of the particle equaling the velocity of the fluid. Of course, we don't forget the velocity of the fluid, by definition, is the vector field. Now, so we are assuming that this vector field represents the fluid flow in that specific way, that the vector field is the velocity. Okay, so all that together, what we have then is a differential equation. Actually, this is a system of differential equations, and if you solve that system of differential equations for what this parametric curve is, then that'll tell you the path followed by the particle, and that is what we call a flow line. Now, bad news, good news. Y'all don't know yet how to solve systems of differential equations, so you can't actually, take a vector field and write down this differential equation and solve that system. You don't have the tools yet. You'll learn how to do that in Math 353, which I guess for most of y'all will be either second summer term or fall, if you're going on to that kind of thing. Okay, or Math 356 if you're maybe majoring in, let's see here, stat or physics or something like that. 356 will also include that. Okay. What we can do, though, is confirm a flow line. So we have an assertion here that this is a flow line, and then it's a flow line for this fluid flow. So again, vector field represents velocity, and the way that you're going to confirm this is you're going to write down the vector field, there it is, and then you're going to take your parametric curve, and you're going to take the derivative of that parametric curve, confirm that that derivative of the parametric curve is equal to the field vector. So it's a matter of writing them down, taking derivatives, and noticing you get the same thing. Everybody happy? Okay. All right. Okie dokie. So let's see here. A quick comment. So I've given you all two different sort of manifestations of vector fields, physical, things that are naturally represented by the abstraction of a vector field. So forces was one of them. Gravitational forces, electric field forces, right? Are vector fields, can be represented by vector fields. And fluid flows, totally different physical thing, also represented very nicely by vector fields. A problem that comes up in this course is that very often students will decide that they like one of those examples better than the other, and will decide, that's going to be the one I'm going to think about. Right? And the problem is that when we get to chapters 6 and 7, there are going to be some applications that we're going to do that unavoidably require us to think about the vector fields in terms of forces. And there will be other examples that we're going to do that will require that we think about the vector field in terms of fluids. So this is not an either-or kind of a deal. I just want to make it very clear. You definitely need to be able to interpret vector fields both as forces and as fluids. Otherwise, you're going to be unprepared for chapters 6 and 7. Okay. All right. Okay, so moving along to section 3.4. This is a weird section. This section introduces some ideas that we're really not prepared to treat yet, that we will treat much more thoroughly in chapters 6 and 7. But right now, we just there's a bunch of tools that we really need in order to be able to make sense out of this stuff. We just don't have those tools yet. Right, so the book introduces it early. I think as a kind of a pedagogical tool to let's plant some thoughts. Let's kind of get certain ideas brewing in your heads, and maybe then by the time we get to chapters 6 and 7, these ideas that we're going to uncover at that time won't seem so weird, and you'll have had time to kind of digest, get accustomed to them. So that's my theory. Now that said, unavoidably, since we don't have the proper tools, several times in this discussion of this section, I'm going to have to say, trust me. And, we'll get to it later, and the ideas, supporting ideas will be there later, and then we'll be able to make a better treatment. Okay, so there we go. Y'all remember gradients? Right, this is one of our notions of a derivative. It's it's many things. It's a notational convenience. It is an algebraic object of a derivative. It is something you do to input changes to get output changes. And it's geometrically natural. It points in the direction of fastest increase. Magnitude is the maximum directional derivative, etc. It's a lot of things. I want to distinguish the gradient, though, from this symbol here that computes it. Right? So this symbol here, think of that as being just the actions of computing the various partials, or arranged as a vector. That's all of that one little symbol is. We call that the del operator. Right? So del is the operator which, when applied to a function, produces the gradient. Right? So does everybody see the difference between the blue operator versus the green result of applying that operator to a function? Everybody's happy with that? All right. Okay, so it turns out that this del operator is a little bit weird to think of it as an independent thing, but it is super handy for talking about some of these objects that we need to talk about. And I'm going to start with divergence. Let's see, here we go. So divergence is this formula right here. And given a vector field that has coordinates f1, f2, f3, divergence is computed by taking the del operator, which again, right here, and applying the del operator, first component of del to first coordinate of the vector field, etc. In fact, you'll notice here, of course, that it's kind of a dot product. And you can literally see the dot product in here that first coordinate to first coordinate, second to second, third to third, add. Right? So this is kind of a weird notation, arguably an abuse of notation, to write it as del dot f as a shorthand for this otherwise uncontroversial formula here. Right? So a little bit of a weird notation, but sure is handy. And it's in very, very common use. By the way, you can also represent divergence as div f. Also common. But for whatever it's worth, and for right or for wrong, in my experience, certainly in my experience as a physics major undergrad, the del dot notation is actually the more common notation. So it's really, really common. It's definitely out there. You're definitely going to see it like that. You may or may not see this. Okay, so what a weird formula. Why would we be interested in such a thing? What does it look like? What does it mean? And here's where I'm going to have to do a lot of hand waving and say, trust me. Right? So the following is not going to make any sense in terms of how did I get this, right? And my goal here is just to describe what the result is, but again, we're not going to be able to motivate it at all. So we're way premature on being able to motivate this. But that said, what the divergence is, divergence in a way, this is going to be a little bit hand-wavy, it represents the amount that the fluid is flowing away from the vicinity of whatever point where you're computing that divergence. Sounds weird. Let me show you an example. I think it'll make better sense. Here is a vector field. Oops. Come on, stylus. There's a vector field. Let's compute the divergence at the origin. Divergence is this formula right there. So we're going to be taking the, per usual, we're going to be taking the x partial, y partial, z partial of the corresponding coordinates of the vector field, which are x, y, z. So that's just following the rule, right? This is kind of doing the, air quotes, dot product here. And conveniently, those are easy dot products, and it's easy to add them up, and the divergence is 3. So the key note here is that divergence is positive. Now, so what would we naturally interpret, given all of this up here, what would we interpret from divergence being positive? Well, divergence says, to what extent is the fluid flowing away from the point 0, and the origin in this case? To what extent is the fluid flowing away from the origin? Well, here's our vector field. Here's a picture of it. And I think it's a pretty easy pitch for me to say, the fluid's flowing away from the origin, right? You can kind of see it happening there. This is about as geometrically obvious of an example as I'm aware. Yes.
Can you give an example of a unit that would be used to represent this?
We don't bother with units. very much in math. That's again, I'm going to file that as somebody else's problem. So very often when you're doing like physics or something, the process goes like this. You decide on what the physics problem is that you're interested in. Pick a set of units. Consistent set of units. So, for example, all of your notions of distance need to be, pick one. Meters would be a reasonable choice, right? But you can't do half the problem in meters and the other half of the problem in miles. That's no fair, right? So pick a consistent set of units, distance, time, mass, what have you. And once you've picked those units, we don't need to deal with them anymore. They're whatever they need to be. And that's, again, a topic for a physics course. But that turns effectively a real-world problem into an abstract problem about numbers. And so we're going to, in a math class, just deal with the abstract problem about numbers and units, or, like I say, somebody else's problem. And by the way, it does get a little weird with divergence and what, the units ought to, how would you really make sense out of this? And it's a digression that's not really what we're here for. Does that make sense? Yeah. Okay. So positive divergence, outward flow. Okay. All right. Now I want to address a somewhat physicsy kind of a question, but this is just for intuition purposes, and that is, so what does that mean physically, right? This is what my vector field looks like. The divergence, I'll do it like this. The divergence is positive. So what's the fluid doing? What does that mean about the fluid? And I think it's interesting to point out that there's actually a couple of different possibilities here. So, for example, we could have a tree that's full of birds, right? And then somebody said boo, and the birds decided to all fly away, right? So the birds are at this snapshot moment, they're all in the process of scampering out of the tree. So what does that mean about the fluid? And I claim that means that the bird density is decreasing because they're evacuating out of there, right? I mean, there was a high density of birds, and as a result of them flying out of there, the number of birds still sort of within the sort of the bounds of the tree, if you will, is decreasing because the birds keep leaving. So you could argue, certainly in that physical case, positive divergence means the density of the fluid is decreasing. Now that's only one possible interpretation, though. So it depends on your fluid. It depends on what's the nature of the fluid that you're talking about. Now here's another perfectly reasonable fluid that could be, at the sort of the source of this picture. What if I had a light bulb at the origin? Forget about the tree. No birds. Light bulb at the origin. It's emitting photons, like so. Right? What does the fact that the divergence is positive here mean? Does it mean that my photon density is changing? No, not at all. There's a light bulb right there. I don't believe we are losing photons. Right? In fact, the light bulb, totally different kind of fluid, the light bulb is continuously generating photons. The light bulb is a source of photons. Right? So, in this light bulb scenario, the fact that the divergence is positive just means that we are creating fluid. In the case of the light bulb, we are creating photons. There's no change to photon density. Right? Does that make sense? Yeah.
What does this mean in the world of forces?
Right. Good question, and not much. So there, not much that I can motivate right now. That is, so it does turn out that there is something very natural. There's a very natural interpretation for gravitational forces and for electric forces. For different kinds of forces, maybe not. It depends very much on the forces. But that's one where, we're really going to have to defer that until we get into Chapter 7, because it's a long, complicated discussion. It's a great question. Okay, so when you're interpreting what the divergence means about your fluid, you do have to understand the nature of your fluid, right? And so in the same way that, when you have a light bulb, we're creating photons. We're not losing photons. We're creating photons, right? And then likewise, if you're thinking about the birds in the tree, right? Here's our tree example. We are literally losing birds. We're not creating birds, right? So, very different interpretation for a very different example. Okay. All right, now just another example. Here's a vector field. Y'all can persuade yourself it looks something like this. Let's compute the divergence. The divergence is computed by this formula, same as on the previous page. Easy partial derivatives. The answer is 0. What does this mean? What's the interpretation, and does this track with our sense for a fluid of this sort? 0 means that for any given little region, let's say maybe a region like this, the fluid is neither emanating outward from nor converging inward toward this region. Said differently, this fluid, there's just as much fluid flowing in as there is flowing out. So this is not a source of fluid, nor is it what we call a sink. It's not like there's a bunch of fluid that's converging inward on it. It's just kind of neither. It's you might say it's a combination of both in the sense that they cancel. It adds up to 0. So again, pretty intuitively satisfying, I think. Okay. All right. Okay. Next concept that I'm not going to be able to motivate. Curl of a vector field. So curl is defined by this formula that has this shorthand. And so given a vector field, you stick the vector field in there like so, and you take del. Of course, there's my del components. Del cross F is this thing called curl. Again, weird formula. Pulled it out of a hat or so it seems, right? We have no motivation for why this should be an interesting thing. But it turns out that it is. And again, I'm going to have to ask you to trust me on this for the moment. We will give a much more significant development of this in Chapter 7. Until then, I'm just going to assert what it is and give you all time to kind of digest the picture. Sans motivation, yeah.
So, with this notation, is this with the partial derivatives in there? Is it a bit like an abuse where it's just like you're multiplying a derivative?
100%. Oh, this is a horribly abused notation. Yeah. Definitely no. So you remember, in fact, when we defined cross product in the first place, we were squirrely about it, right? Because you want me to take a determinant where these entries here aren't even numbers. So I had to confess this is what we call a symbolic determinant, because these aren't even numbers. And now now we've got 2 of the 3 rows and they aren't even numbers, right? So you're absolutely right. This is symbolic kind of nonsense if you get up real strict about it, right? But it is extremely convenient as a shorthand for, otherwise you would have this weird formula that seems to be disorganized and kind of random. Yeah. So, I'll get right with you. This one, let me point out how to compute this thing real quick. So, for example, if you wanted to compute the first coordinate, well, there's our E1. The first coordinate of the curl, then, following the usual rule, is going to be, well, this little symbolic determinant, which, of course, is going to be the y partial of F3 minus the z partial of F2. That is our first coordinate of our curl vector. And then likewise for the second coordinate, likewise for the third coordinate. Yeah?
So this only really works in 3 dimensions?
Correct. This is a peculiarity of 3 dimensions. That's right. Yeah. Okay, there is something highly similar to this in 2 dimensions. I personally think it's sufficiently different that I prefer not to use the same name, but and I have a different name for this kind of sort of thing-ish, if you will. I don't call it curl. I call it something else. But plenty of people do call that other thing curl. So in a sense, I mean, certainly in terms of the usage of the word, there is a two-dimensional version, but it's not this formula. It's a different formula. It's just that it has a similar interpretation. Yeah. Okay. Okay, so again, this is an arbitrary-looking formula, and again, I'm not going to be able to give you any motivation. I'm just going to assert what it is that curl represents geometrically, and here it is. It represents how much and around what axis is the fluid circulating? To what extent is there kind of I like to think of them as little tornadoes, right? Little eddies, where the fluid is kind of going around, where, you know what I mean? I mean, so some people call it a spinning of the fluid, some people call it a twisting of the fluid, a rotation of the fluid, something kind of like this, per my hand gesture here. Okay. So I have given you no reason to believe that that's true, but let me show you an example. And again, we'll make much more sense out of this later. Here's an example. Y'all will recall this vector field. Well, we wrote down something very similar to this. We wrote down sort of a two-dimensional version of this. And it has, if you will, fluid kind of going around in sort of circles. And now that we have a three-dimensional version of it, it's likewise at sort of all altitudes. So this is really representing something that you might call a little tornado, where the fluid is going around, it's kind of going around the z-axis. Yeah. So let's compute the curl. I wanted to be in this mode. The curl, computed by this formula, you gotta go through and play the game, take this partial of that, make it this coordinate, etc. And you end up with this as the curl vector. And now let's draw the curl vector on there, and notice it is pointing straight up. And as predicted, this is pointing in the direction of the axis that the fluid is circulating around. And this magnitude of 2, that magnitude of 2, in some sense is telling you how much. Is this a powerful tornado? Is this a violent rotation around the z-axis, or is this kind of a gentle rotation around the z-axis? Again, we don't have units for that, so I can't make that precise, but just the idea is that the greater the magnitude of the curl vector, the stronger the rotation is around the axis. And again, let's not worry about units. Okay. Everybody buy it so far? So, why curl does this? To be discussed later. What this is that I'm claiming curl does is what I'm hoping you'll have digested here. That it's describing the rotation by way of what axis the rotation is going around. Okay. All right. So here's a nice little example, and I'm going to call this one an easily satisfying example, because you've got your flow lines for this vector field that are all kind of like this. And of course they go kind of both different ways, as I'm sort of drawing here. There's our vector field, and how much rotation do you see in this fluid here? I would propose you probably would suspect there isn't any rotation there. And that tracks because, well, you compute the curl and indeed 0. So no curl, no rotation of the fluid. Okay. Let's be careful about this though. This next example is going to look similar, but it's importantly different. This next example, here we go. We got a vector field, and the flow lines are kind of like this, and then they sort of change direction. But nevertheless, all the flow lines are straight lines. It is tempting to say that there's really nothing rotating. There's no rotational aspect of this fluid. Crying out loud, the flow lines are all straight lines. Here's the thing, though. let's compute the curl. Curl ends up being not 0. Curl is a downward vector. How could there be an indication of a rotational aspect of this fluid if no particle in this fluid is going in anything other than a straight line? And the answer is this. So there is a hidden, there is a hidden rotation here. So imagine this being a fluid, and then imagine you were to take I like to think of this fluid as being like the surface of a river. And you drop a dead leaf into the river, and it kind of floats, and it just goes along with the river, right? But as the dead leaf floats along, it's also going to have a twisting to it. You may have even seen this. You drop a leaf into a creek or something. It doesn't just move in a translation sense. It kind of rotates as it goes. The reason for that is, and you can see it right here in this picture, it's being pushed harder on that side than it is on that side. And next time you're at the grocery store, take your shopping cart and push harder on the right and less hard on the left, and your cart's going to start to turn, right? So unsurprising then that we would expect, given the nature of this vector field, that leaves will rotate as they flow downstream, as it were. So that is the rotational aspect of this fluid that the curl is picking up. It's, again, kind of a hidden rotation. So a big takeaway that is, by the way, going to show up on a homework exercise. I can't remember when exactly, but sometime, I just can't remember when. Anyway, so at some point, there's going to be a homework exercise where there's a vector field kind of like this. The flow lines are all straight lines. And you're going to need to figure out how to get the fact that there is a non-zero curl to line up with the fact that the flow lines are all straight lines. And let me just go ahead and give you the answer right now. How could the curl be non-zero if the flow lines are straight? The answer is curl is not defined in terms of flow lines. It's just not. Right? It's a fundamental misunderstanding of curl to think that it's about the shape of the flow lines. It is not about the shape of the flow lines. It's about this more difficult to put our finger on concept of how are things rotating that are moving within that fluid. Okay. All right. And again, I mean, I'm doing a lot of sort of hand waving kind of stuff here, and I'm going to be able to make all of this much more precise when we've defined something called a vector line integral, for example. Will make all this make much more sense. Okay. So real quick now, there are some various additional facts. Here are some additional facts that are in the book. You can check for yourself, for example, that the curl of a gradient is always 0. That's an easy little computation. A less easy computation, in fact, a pretty hard. You can't actually. This is a weird one. But if the divergence of a vector field is 0, weirdly, that actually tells you that that vector field is a curl of something else. It's really hard to see that coming. It's really hard to actually prove it, even if you have somehow got some sense for this. So, difficult fact to prove, but still true. And there's various other relationships between gradient and curl and divergence. I like to kind of unify them all in the following sense. There's some really deep ideas that I'm not going to be able to talk about in this class. Extremely deep. Sufficiently deep that when mathematicians first started writing down the ideas that we're playing with here, to the time that this level of this organization of the ideas got really sort of solidified, about 100 years. of really smart mathematicians trying to figure out how to make these puzzle pieces fit together. So this is a extremely sophisticated and deep idea that I'm only, I would say, scratching the surface of at most. But the easy way to think about it is think of gradient and curl and divergence as being kind of like little Legos. And you'll just notice that they fit together like this. So what comes out of the gradient operator is always a vector field. And hey, a vector field is also what goes in to the curl operator. So these pieces fit together. And likewise, these pieces fit together. What comes out of the curl operator is the same kind of critter that goes in to the divergence operator. So what we have here is called a sequence of operators. Why do I keep hitting the wrong button there? This is a sequence of operators, and it turns out this is a special sequence. This is what we call an exact sequence, which is, again, more sophisticated stuff that I'm not going to be able to talk about, but give me 2 seconds. The big idea of what I mean by an exact sequence is pretty much that what I like to summarize as all of the lifetimes are 2. Example. If you have a function, let's see, how am I going to do this? Yeah, okay. If you have a function and you compute its gradient, that will give you a vector field, but then if you take the curl of that vector field, you will get 0. So I call this a lifetime. The lifetime is 2 in the sense that from where we started to where we ended, namely where we got 0, I like to think of 0 as being kind of death in this metaphor. If you'll, again, kind of, it's very, hand wavy, because this is not a precise thing, right? But if you think of 0 as death, then from birth to death was 2. And it will always be 2. And so here's another version of this, another version of the lifetime being 2. If you have a vector field, and if the curl is not 0, that actually tells us 2 things. First of all, the lifetime's got to be 2. That means its divergence is going to have to be 0. But it also means that if this is where the death happens, then this must be where the birth happened, which means that there cannot be a anti-gradient, because that would make a lifetime of 3, which is not allowed. And so again, the lifetime is 2. Everybody see what I mean by lifetimes are 2? Again, this is all very hand wavy. So anyway, you can take this concept of lifetime as 2 and make various different mathematical results out of it. These are just a couple of those mathematical results. Yeah, you had a question. Sorry.
Wait, go to the thing. So So I had a question first about, well, if you had a function and then you got its curl of the vector.
I'm sorry. We got a function and then what? You can't take curl of a function.
Okay, yeah. I think I was just getting confused by the.
Yeah, you gotta stick with this, this sort of connection of Legos, as it were. So if you're going to apply the curl operator, you can only do that to a vector field. Yeah, which, by the way, if you think about it, that's the only thing. What was
the implication? You said vector field, you get the curl of the vector field, and then if you get the divergence of it, then it would be 0.
Yes.
And that implies that a vector field can't have a.
Well, let's consider the scenario where the vector field, where you take curl, you take divergence, then you get 0. And specifically this one here, not 0. If there were an anti-gradient, then its gradient would be non-zero, that curl would be non-zero, and it would be all the way over here to the divergence before you finally get 0, and that would be a lifetime of 3, which is not consistent with this statement. Right, so this is what we mean by an exact sequence. So all the lifetimes are 2. If the lifetimes have to be 2, then that can't be there.
Mm-hmm.
Does that make sense?
Yeah.
Yeah. So it's just kind of this is not a proof. Don't look for rigor here. This is just this is an assertion, right? I'm saying all the lifetimes have to be 2, with some minor exceptions that are not worth talking about. So I'm just asserting that that's the case. Don't look for why.
Why is this the order that we do it in?
Deep magical reasons that are way beyond this class.
Okay.
Yeah.
So,
no, I understand that the Legos will fit together in other orders. This is the one that actually this is the one that makes these ideas work.
Mm-hmm.
Yeah. Okay. Yes.
This is a clarifying question about. This is when we're looking at the gradient in relation to the calculus of vector fields. This like when you were talking about like the gradient like and it's like perpendicularity to like level set.
Yeah. Same gradient.
I was like
same.
But this is like, and then this is specific. Is this specific to the view of like when you're viewing a gradient as a vector field?
Oh, yeah. That's right. So that's what writing this, the interpreting gradient as something where a function goes in and then a vector field is the result that's produced.
And then looking at it like as like a level set and looking at it as a function. It's just different.
It's still the same gradient operator, right? But I mean, the point is if a gradient is a vector field. A vector field means that at any point there is an actual vector there. It remains that single vector at that point, that is perpendicular to the level set of that function, sure. All that's still true. It's the same gradient operator. It's just that we're not interested in level sets in this conversation, that's all. We're just, it's all that stuff is still true. This is the same gradient. We're just talking about another collection of neat facts about this same gradient. Yeah. Okay. All right, so I always feel weird talking about this stuff because, again, I'm just pulling this seemingly out of nowhere, right? Y'all just have to trust me that this is true. And on the topic of trust, let me talk about this asterisk right here. You do have to worry. There are some what we call regularity issues. What if the vector field isn't continuously differentiable? Oh gosh, all these kinds of things. If you're worried about continuity and differentiability and stuff, it does get weird, and that's a more difficult conversation that we can't go into, right? So I'm going to assume that everything in sight is smooth, infinitely differentiable, no regularity problems of any sort. But anyway, with that said, I recognize that I'm asking y'all to trust a lot here, and nothing that I'm on the page is rigorous, and
So this is just something we have to take.
Absolutely, yep. I learned this stuff in graduate school.
Mm-hmm.
Yeah.
And what's the implication with if a function has a gradient?
Yes.
That gradient can't have a curl, or its curl is 0.
Its curl is 0. Yeah.
So
and that's an easy calculation. You can do that yourself. You can take a gradient, compute its curl, you will get 0. In fact, that will work for all, appropriately regular. In other words, let's not worry about continuity problems and differentiability problems, but just generically for nice functions, always 0. Yep. Okay, so what I want to persuade y'all of at least is, if again on the assumption you're willing to believe me, right, then this is a real eyebrow raiser. Curl, this weird formula we wrote down, has this powerful connection to the gradient that we've already seen have lots of utility and naturality. So this should be pretty persuasive that, whoa, this curl thing is probably also natural because of how powerfully it connects to gradient, etc. Okay, so, and there's much more of this. And again, in chapters 6 and 7, we're going to do much more with these ideas. And so this is just a tip of the iceberg, scratching the surface, and more to come later. Okay, so that finishes chapter 3, and we move on now to chapter 5. What happened to chapter 4, you ask? Chapter 4, we are going to cover, at least sections 1, 2, 3. I forget if there's anyway, we're covering some stuff in chapter 4. We are pushing it off to the end of the course for what I'm going to call strategic reasons. It turns out that chapters 6 and 7 are challenging, and there's a tremendous amount of ideas. It's very geometric. It's also very algebraic. There's a lot to digest. And so my strategy in this course is to get to chapters 6 and 7 as fast as I possibly can without going in, unprepared. Right? And so anything in this course that I don't think we really technically need for chapters 6 and 7, I'm going to do it after chapter 6 and 7 so we can get there as soon as possible. So y'all can have as much time to digest chapter 6 and 7 as possible. Chapter 4 is about the only thing that isn't prerequisite to chapter 6 and 7. So 4 waits until later. And we move on to chapter 5. We're going to talk about integrals. Reminder, back in chapter 2, there were various different kinds of derivatives. The very first one that we talked about was partial derivatives. And I gave you all kind of a warning in advance that, hey, we're starting with it because it's easy, not because it's really fundamentally the way you ought to look at it. Right? And I hope you all have a good perspective on that now, that, the best way to think about a derivative in multivariable calculus is that it's a matrix. That's what turns input changes, which are vectors, into output changes, which may also be vectors. So that doesn't show up in partial derivatives. We do partial derivatives first because it's accessible and convenient and useful various different ways, and it's just a nice sort of segue in a sense. So anyway, in the same way here, the very first thing I'm going to do here in integrals is not really how you ought to think about integrals. I'm going to start with something that's accessible and convenient. And we're going to develop a more sophisticated point of view on this later, possibly later today. We'll see. But anyway, here we go. Okay, so I'm sure y'all remember this, right? If you have a rotated surface, right? So specifically you have a curve in the XY plane, which you then rotate around the x-axis, and that generates this surface. And you could ask, all right, how do I compute the amount of volume? What's the total volume inside of that surface? And how would you compute that volume? Well, I would chop it up into little pieces, as we often do when we're computing integrals. There's a bunch of little pieces of volume that look like that. I'm going to call that dV. And then I'm going to take an integral from A to B. I'm going to add up all those little blue, coin-looking cross-section things, right? And the sum of the volumes of those little pieces of volume gives us the whole volume. And then now, how much volume is there in a little piece? Well, in any one of those little pieces, I've got a picture that looks kind of like this, and I can talk about area and thickness, and conveniently, now we get lucky here, the cross-sectional area just happens to be something that we understand. The cross-sectional area is pi r squared, and convenient little geometry argument, and there it is. There's that cross-sectional area. That's essential to being able to make this argument work. Everybody happy with all that? Flashback to Calc 2 or Calc 1, depending on where you took it? Okay. All right, so let's try to apply that same idea now to a different question. Here's the different question, now a multivariable question. Here we're going to be looking at a graph. Oh, again with the highlighting, sorry. Graph. Right? Graph of a multivariable function. Here we have a function of x and y. The graph is this surface here. And if I wanted to compute the volume under that surface, let's just say, how would I compute that volume? Oh gosh. I would could attempt to compute this volume by saying, okay, well, we'll look at these little, I like to think of it as a slice of bread in this great big loaf of bread, as it were. Talk about what's the volume of that little slice of bread. I will then add up from C to D as I move along the y-axis. So this is a strategy of how I could conceivably compute that volume. The problem is that volume here has a cross-sectional area which is not a handy-dandy, familiar, geometric figure. It's not a disc, it's not a square, it's not a triangle. It's got a weird curvy top, and this is not a high school geometry type of an area. So we're kind of arguably out of luck. Right, trying to rip off the idea that we did here hinged critically on the cross-section being a disc, for which I knew the formula did not work out. Okay, so here's where a lot of people would throw up their hands and give up. We're going to push on after all, because if you think about it, that cross-sectional area, no, it's not a disc and it's not a various other things, but it is, however, the area under a curve, right? This curve here, the cross-section of our original surface, specifically the cross-section where I fix a value of y, right? So y is not allowed to change. And then I imagine that I let x go from A to B. So x now is going to be thought of as my variable. And with y fixed, and with x going from A to B, there's a curve here that is the cross-section of our surface, and we're literally interested in the area under the curve. And we know how to compute the area under a curve. It's this thing right here. Nothing to it, after all. So high school geometry doesn't cut it, but high school calculus, right, kind of does. Pretty much, right? So now, don't lose track of what is happening. It is really easy to lose track. A lot of people get very upset about the fact that there's two variables in here. I don't know what to do with all those y's, right? You got to keep in mind what's going on is that y is constant, right? Y is fixed. Said differently, it's only for a single specific cross-section happening, of course, at a single specific value of y that I want to compute this area. So this is not two variables inside of there. Right? It looks like two variables, but it isn't. Y is a constant. And so you're going to treat that y like it's k or something, right? It's not actually a variable. It's just, it's a late alphabet character, but it's a constant as far as that integral is concerned. Is everybody happy with that? Okay. All right. So that's how you compute your cross-sectional area, and it's all over but the shouting. Cross-sectional area times thickness, right? With how thick is our, let's see here, no, I needed a different color, blue, okay. How thick, dy is our little slice of bread here. Right, there's a dy thickness, and there we go. And this is, I want to recognize, a very weird looking expression. We have an integral of an integral. Creepy. Now, let me erase all the colors and remind us what is going on and what all this means. What I'm going to call the outside integral represents this process of going from C to D. Y is going from C to D, for which purpose we then get cross sections like that, right? These little slices of bread, as it were. That's what the y integral is representing. And then, for any given value of y, x goes from A to B so that I can compute what that cross-sectional area is. That's weird, right? So again, we're literally doing an integral in the y direction, and then elsewhere in the calculation we're doing an integral in the x direction. Is everybody on board? Okay, so this is called an iterated integral. Never really liked that term. Iterated to me suggests we're doing something repetitiously. I recognize we are doing an integral of an integral, and that sounds like a repetition, but very importantly, they're very different integrals. A dx integral in the x direction, a dy integral in the y direction, totally different things. So I don't really like this term. I at one point tried to popularize the term nested integrals, because it's literally an integral inside of another integral. I thought that was a little more clear, but it didn't take off. That was 20 years ago. I'm officially giving up. Anyway, iterated integral. Okay. All right, and just a little bit of terminology. Let's talk about which is the first integral and which is the second integral. Which is the first integral here? Well, it really kind of depends. From our slicing standpoint, this was the first one we wrote down. We first took our loaf of bread and we said, look, slice it perpendicular to the y-axis. That's where our dy integral came from. And only after that did we start thinking in terms of x integrals. So we wrote down the dy integral first. But from a computational standpoint, when we get to computing this, you have to compute your dx integral first. I can't compute my dy integral, yet I don't know what its integrand is until I compute the dx integral. So computationally, you have to go sort of inside out. Structurally, in generating it, you have to go outside in. As a result of this term, the idea of, which is the first integral and which is the second integral, completely unclear. So I advise you to absolutely never use first and second in distinguishing these integrals from each other. I do like the point that you can view the dy integral here as it's the one on the outside. That's unambiguous. It's very clear. dy is the outside integral. Dx is the inside integral. I'm all for it. Is that cool? Okay. Alrighty. Oh yeah, and then again, don't forget, I've already made a big deal out of this, but let me say it again. How do I deal with this dx integral? How do I deal with the fact that while the differential variable x is in there, so is y? How do I deal with this extra seeming variable that there is in there? It isn't. Y, what you might call the outside variable, y, is a constant because of where this picture came from. That inside integral came with the understanding that we were fixing a single value of y. Okay, so good general rule to remember, when you have an iterated integral, the outside variable is constant for the purposes of the inside integral. All right, let's do one. Here is a graph of a function of two variables. It's a part of a paraboloid, and I want to compute the volume under that graph sitting over this rectangle here. And before I go on, let me explain this notation. I know this is a weird looking notation. What do we mean by 0, 1, cross 1, 2? This is not a cross product. This is just a shorthand notation as follows. 0, 1 represents the range of values of x. And let's see here, color choices. I'll use red. 1, 2 represents the range of values of y. And so given those x values and those y values, that defines a rectangle. Does everybody see what I mean there? So we're going to be using this notation significantly, so heads up, be on the lookout for it. That's what that means. Okay. All right. So how do I compute this volume? And good news, we've already basically answered that question. This volume is this iterated integral. The function whose graph we were looking at is the integrand. So off we go. Plug and chug time. Here we go. How do we take the antiderivative of x squared? Well, that's 1/3 x cubed. Cool. How do I take the antiderivative of y squared? Here's where a landmine is. Very common landmine for students to step on. Tempting to say 1/3 y cubed, because that's how you do it, right? That's how you do antiderivatives. But no, you've got to remember the outside variable is constant for the purposes of the inside integral, and it is the inside integral that I'm doing right now. So as I work out this inside integral, I have to treat y like a constant, because it is literally a constant for the purpose of what I'm doing here. So this is not variable squared, right? That is constant squared, aka this is itself just another constant. And the antiderivative of a constant is that constant times the variable, in this case, x. Everybody with me? Be real careful, right? That's part of the student's job when you're dealing with this kind of stuff, is to keep track of which variables are playing what roles at which point in the calculation. Outside variables are constants for inside integrals. Okay, and there's only really one other little potential landmine here. We got oh my gosh, my stylus. Got an antiderivative there, and then let's see here. We're going to evaluate from, our bounds are from 0 to 1, and you'll notice I have written not just 0 and 1 here. I have written explicitly x equals 0 and x equals 1. And let me tell you why. Without that, if you just put just the 0 and the 1, you'd be surprised how easy it is, as you're plugging in the 1, to accidentally plug it in for the y also. It's just super easy to accidentally do that. Of course, that's nonsense. Y is a constant. It's like a k. You don't plug in anything for it. It just stays what it is. Well, so I find it helpful to me to write x equals 1, and then when I start trying to plug in that into a y, then wait a minute, no, this is y, not x. And I stop myself before I do it. You don't have to do that. I think it's a nice little, it costs you a second and a half to write x equals twice, right? And it's going to save you accidental mistakes. Okay, it's all over but the shouting. Keeping in mind, we are, my stylus, we are, oh my gosh. There's our inside integral. That's what we're computing when we plug that in. That's what we end up with here. And now we'll proceed to the outside integral. The outside integral is the dy integral. Y is now a variable again. It's the variable for this outside integral dy. And so, antiderivative, plug it in, blah, 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 and answer. Everybody good? Okay, real quick exercise for y'all to do on your own. What if you were to slice the other way first? Now, let me go back over to here, point out what I'm talking about. I had this great big loaf of bread here, and I was doing my slices first perpendicular to the y-axis. I was doing my dy slices, you might say, first. What if I took a totally different slicing strategy? What if I sliced perpendicular to the x-axis first? My slices would look like this, approximately. And I could write that down as an integral. I could compute the cross-sectional area. The cross-sectional area then, if you think about it, would be a y integral. Right? That would be giving me the area under this curve. And what happens when you write all that down? And all it is geometrically a sort of a opposite slicing order. How does that affect your resulting calculation? And again, I think this is a really good exercise for you all to do on your own. The punchline is, all it does is it reverses the order of the integrals. It switches. What had been the outside becomes the inside. What had been the inside becomes the outside. So now, in particular, what had been the outside becomes the inside. And notice that applies both to the bounds and to the differentials. Right? So you got to do, with the hand waving, if you will, you got to do this. Don't do this. Right? That's wrong. If you just move just the bounds, or if you do just the differentials, that's not the same. Completely different. Right? But if you do them together, it's fine. Okay. All right. I am going to throw out a word of warning. This only works when the domain is a rectangle. That's all we've even entertained here. Is we're doing integrals on. We're computing the volume under graphs over rectangles. We have not entertained different shapes yet. If I want to compute, same graph, but now I want to look just at the part that's sitting over a disk here. How would I compute this volume? Oh, that's a much harder question. That's different. And we'll be getting to that next week. Okay. All right. And this punchline does not work. This move where you move the outside to the in, the inside to the out, doesn't work at all. Okay, last thing for today. I want to point out that when we did single variable calculus, the tool that we used to compute the area under a graph worked just fine for computing all sorts of other things. We computed, the mass of a one-dimensional rod, or we computed the number of bacteria in a petri dish, or various other examples that you all saw in your Calc 1 classes. You would think then that because this is a tool that we use to compute now volume under a graph, wouldn't you think that the same ought to apply to other examples, like how would I compute, mass that's contained in an area? Analogous to computing mass of a one-dimensional rod. Just following the pattern, it feels like it ought to. Very importantly, it does not. And I want to point out kind of how the argument crashes and burns pretty badly. Let's look at our existing construction. Here's our iterated integral. And the very first thing that I have to sort of put together to start making sense out of it is f times dx. And of course, f is a height, and dx is what you might call a length. And so that is area. And I can talk about doing an integral where I'm adding up a bunch of little pieces of area because I understand areas. I know that that's how areas work. If you have one area and another area, well, the area of the whole is this area plus that area. Of course it is, for crying out loud, right? Well, golly, that's a very special feature of area. It is an accumulating quantity. The whole is the sum of the parts. Sum, specifically, of the parts. This is not true of other quantities. For example, let's take just an easy one. Density. If I know the density of this thing, and if I know the density of this thing that's right next to it, and I want to ask what's the density of the union, you don't add them. So density is not an accumulating quantity. All right, well now let's consider how would I make sense out of this thing here if I'm looking again, first thing I would have to understand if I want to write down this expression here, well, I would have mass per unit area times length. And I don't know what that is. That's not something I have pre-existing intuition for like I do with area. I've got a death grip on the understanding of area, right? But this thing, mass per unit area times length, what does that even mean? Mass per unit area is designed to be something that you multiply by area. When you multiply it by something, it's not area. I don't know what we're talking about. Is this even an accumulating quantity? Can I even make sense out of taking an integral of that? Oh my gosh, who knows? This is not clear. So this argument, the iterated integral argument, cannot be used to compute anything other than volume specifically. This expression only for volumes. And we're going to have to figure out a totally different way to answer questions like, how do I compute a mass? We're going to have a completely different strategy for doing that. And I'll bet you I'm out of time. Yeah, this is a good place to end. Okay, see y'all later. Have a good weekend. And I hope to have grades for the exam returned to y'all by the end of the weekend. No promises, but I'm going to do the best we can. All right, see y'all later.